a heavy machinery component begins its life as little more than dirt and scrap. In this dimly lit workshop, the foundation of a high-tolerance piston starts with the casting sand. The craftsman pours a dark, viscous binding agent into damp soil, blending it thoroughly by hand and shovel. This mixture must achieve a specific consistency to hold a rigid shape under extreme thermal shock. Too dry, and the mold crumbles during the pour. Too wet, and trapped steam will cause the molten metal to violently fracture. The binder coats every grain of silica, creating a matrix that can withstand the intense heat of liquid iron and aluminum without losing its dimensional accuracy. After packing the sand tightly into the rigid frame, the craftsman prepares the cavity surface. A fine parting dust is pressed firmly against the compacted soil. This dry powder acts as a crucial barrier, ensuring the metal pattern can be withdrawn later without tearing the fragile mold walls. The cylindrical core is then seated in the center. It defines the negative space where the molten metal will flow. Every grain of loose material is cleared away from the edges. A single errant piece of debris could create a void in the final casting. The process shifts to a ground pit furnace, where a crucible of scrap is buried in glowing charcoal. A sunken hearth concentrates the thermal energy inward, driving temperatures high enough to break down solid metal. The worker uses a long steel rod to manipulate the fuel bed and ensure an even distribution of heat. Managing the draft in an open-air pit requires constant attention. If the fuel starves for oxygen, the melt stalls. If it burns too aggressively, the crucible itself risks degrading before the scrap reaches a fully liquid state. Has completely liquefied, reaching the optimal pouring temperature. Timing the extraction is critical. Pulling the crucible too early leaves solid inclusions in the liquid, while leaving it too long oxidizes the valuable alloy. The glowing vessel is carefully lifted from the pit. At these temperatures, the liquid emits a blinding orange light, illuminating the dark workshop as it is carried to the mold. The surface slag is skimmed away to prevent impurities from entering the casting. Then, the molten material is poured in a continuous, unbroken stream. A steady flow prevents cold shuts, where cooling metal fails to fuse properly inside the cavity. The mold is immediately capped with a heavy lid to maintain internal pressure and control the cooling rate. Slow, regulated cooling allows the granular structure of the metal to stabilize without warping. After the rough casting is hammered out of its shell, the true machining begins. The raw block is mounted securely in a lathe chuck. The first pass of the cutting tool removes the oxidized outer skin, known as mill scale, revealing the pristine aluminum beneath. This initial cut establishes a true cylindrical reference point for all subsequent measurements. Operating the lathe requires a balance of speed and feed rate. If the tool advances too quickly, it shatters against the surface, leaving deep ridges. If it moves too slowly, the friction generates excessive heat, potentially distorting the workpiece. The sharp carbide tip shears away continuous ribbons of waste material, transforming a coarse, sand-textured block into a bright, geometrically perfect cylinder. With the outer diameter established, the operator cuts a deep, precise step into the cylinder wall. This groove reduces the overall mass of the piston while retaining structural integrity at the critical wear points. The tool geometry determines the profile of the cut, leaving a sharp, clean transition between the two diameters. Next, the interior is hollowed out. Removing material from the center lightens the component significantly, which lowers rotational inertia when the piston eventually fires inside a running engine. The internal boring tool smooths the inside walls, clearing away any remaining casting imperfections. The interior space is cleared of debris with a metal pick, ensuring no hidden chips interfere with the final passes. The tool post is recalibrated for a finishing cut. Unlike the aggressive material removal of the earlier stages, this fine pass barely grazes the metal. It is designed to shave away microscopic high spots and leave a uniform, polished finish. The depth of cut is minimal, requiring exact tension on the lathe carriage. This smooth surface reduces friction against the cylinder sleeve, extending the life of both components. The fine shavings fall away like dust. The piston is now geometrically sound, holding tight tolerances that rely on the operator's experienced hand rather than automated programming. the critical ring grooves must be cut to exact specifications. The machinist uses a caliper to confirm the running diameter before engaging the parting tool. These narrow channels will hold the compression and oil rings, forming the vital seal that gives an engine its power. Machining them requires constant lubrication. A few drops of oil from a plastic bottle flood the cutting edge, dissipating heat and flushing away chips that could gall the sensitive aluminum surface. Heat is the enemy of precision here. If the metal expands during the cut, the groove will shrink once the part cools. The operator takes his time, pulling the piece from the chuck for frequent visual inspections. He relies on tactile feedback through the handwheels, feeling the resistance of the metal change as the tool bites. A final, light pass clears any burrs from the edges. Visual checks are secondary to the physical fitment test. The craftsman seats a steel compression ring into the newly machined groove. It must slide in smoothly, but without lateral play. If the gap is too loose, the engine will suffer blow-by, losing compression and burning oil. If it is too tight, the ring will bind and score the cylinder wall when it expands under running temperatures. The smooth insertion confirms the lathe work was flawless. A final drop of oil is applied to condition the raw aluminum and prevent atmospheric oxidation while the component waits for installation. The foundational turning phase is complete. The piston is moved to a drill press to bore the wrist pin holes. These lateral openings will eventually connect the piston to the connecting rod, transferring the explosive force of combustion downward to the crankshaft. Alignment here is unforgiving. The holes on either side must be perfectly concentric, or the piston will sit crooked in the cylinder bore, leading to catastrophic failure. The drill bit descends, biting into the thickest part of the casting. The operator holds the piece firmly against the bed by hand, substituting physical strength for mechanical clamps. As the bit cuts through the alloy wall, it generates immense friction. Drilling deep holes in soft aluminum poses a specific risk. The metal chips tend to weld themselves to the flutes of the drill bit. This heat buildup causes the bit to wander off center, ruining hours of careful machining in a matter of seconds. To combat the heat, a second set of hands provides steady liquid cooling. Pouring water directly over the cutting zone flushes the aluminum chips away before they can fuse. The water absorbs the thermal energy, preserving the temper of the high-speed steel drill bit. With the temperature controlled, the bit punches cleanly through the far wall, finalizing the structural boring. Machine tools provide geometry, but hand tools deliver the final edge. The worker uses a hand file to break the sharp corners around the newly drilled holes. A heavy burr left on these edges could scratch the wrist pin during assembly. Following the file, fine grit sandpaper is wrapped around the body of the piston for a final manual polish. This manual abrading knocks down any microscopic ridges left by the lathe tool. A slightly scuffed surface actually retains engine oil better than a mirror polish, ensuring lubrication during the critical break-in period. The assembly is the moment of truth. The finished piston is wiped clean of abrasive dust and aligned with its mating components. It slides flawlessly into place, operating with zero binding and zero loose clearance. What began as a pile of dirty scrap metal and loose casting sand has been forced into a high-tolerance, functional pile. Every deliberate pass of the lathe, every measured drop of oil, and every controlled pour of molten aluminum accumulates in this mechanical fit. It is a testament to foundational manufacturing. The shop relies on raw skill and analog tools to produce a part that matches the exacting standards of modern machinery. In the end, structure, material, and human routine operate as one system, taking the discarded and making it vital again.